Yeah, so as some of you might have read on Hacker News or Reddit, we have developed a new programming language which recently came out of stealth mode about 6 weeks ago. And well, you're experts in the field, so you definitely know that concurrency is really here to stay. We're not moving back to the single core world. Your phone is essentially a multi-core system. Your workstation is a many-core system, and effectively your data center is a supercomputer. So it's evident when you write a program, you preferably want to scale it to a virtual infinite core count, or at least you want to write a program and run it on your notebook and then run it on your SGI supercomputer or run it on your gigantic data center without actually changing the source. For this to really work, we're the opinion that, well, not only us, but a lot of people in the programming language community are the opinion that languages should be really naturally concurrent. So the language itself should really focus on solving this problem rather than being a library implemented on top of other languages. So the goal is generally you want to develop software efficiently and reliably, and we actually had just a very interesting conversation outside this room. You want the programming language to be programmer-centric, so the compiler should give feedback to the programmer and help the programmer actually succeed. So the why question is really something really important to us, and that's one of the messages that we want to transport today. Because the why question, especially for a small startup like us, is where we take the inspiration from and where we take the motivation from. So we believe this is a seriously important problem, and if you can sort of help the programmer become more productive, that's actually a big deal. There are various really hard problems that come with concurrent programming. So you have all kinds of different performance issues. When you use locks, it's really hard to have high performance code with locking, because either it's not fine-grained or you try to get it fine-grained and then you run into serious problems afterwards. And then you have the various things that come into combination with how operating system works. So you have priority inversion, where stuff happens that you actually don't want to allow. And then you go right down to hardware stuff, where you have fault sharing, all kinds of cache coherency problems. So you can really see that just because you're now moving to a world where you have multiple cores on your CPU, you get problems on all kinds of different levels. So you get it on the thinking level, you get it on the performance level, you get it on the hardware level, and this is a huge challenge because of exactly that reason, because it touches every single part of your basically entire IT stack. So not only that you run into performance issues, you run also into correctness issues. So when you use locks, you can easily still get it wrong, run into data races. So synchronizing concurrent access to memory is tedious. Deadlocks is a gigantic problem, and locks basically expose you to this issue where you sort of two different things are waiting for each other. And debugging those two kind of problems is really tough, even for the most experienced programmers. And then we sort of get also to the softer things, exceptions. So you all know the typical thing when your program crashes because of an uncaught exception or null-pointer access or division by zero, etc., etc. And then there are also the kind of C world kind of things where reusing memory can be problematic. So you have null checks in your program, but it doesn't necessarily help you because you're reusing old memory and your program is starting to crash. And of tracking these kinds of problems, we believe it is a serious challenge for languages. Null-pointers. Null-pointers is it's a really interesting thing. And Tony Hoare, who is one of the Turing Award winners, actually says this was his billion-dollar mistake back in the days when he was really started to think about programming. He sort of thought it was a good idea to go for null-pointers because they were easy to implement, and it caused all sorts of interesting problems actually. And we are sort of going to talk a little bit in great detail and under the hood how our compiler and language works and what we do about these kind of things. Now, of course, you can always say, well, my program can have problems. I can always debug it. So maybe I'm a really experienced programmer. I start a debugger, and eventually I'll find the problem. The real issue is that, especially when you're in the world of data race bugs or memory-related issues, debugging is extremely hard. one of the really important reasons for this is that when you, for example, start to debug data race bugs, you have to deal with time and space at the same time. And I'm personally of the opinion that this is really difficult to do for the human brain. Especially because you have a notion of non-determinism in the debug process, which is not really making you productive. And although we have debuggers, which allow us to find a lot of bugs, real-world systems still crash. And it turns actually out that the total cost of ownership of software development actually is being used to 50% just for debugging and finding defects. So it has a serious business impact in order to get the language right to help the programmer make fewer mistakes or remove some of the bugs at compile time, essentially. So you all know this, you're experts in the field. So IT projects are rarely on time, and they are often over budget. And we started to think when we first started thinking about implementing a new language, is why is that actually the problem? Because I don't think it's management related or it's the development process, because companies are actually really good at this. Companies have become really good at managing people and managing software projects. So what is the problem that we are still seeing budget and schedule for software project is an issue? And we're basically focusing on 2 points for this presentation today. Obviously bugs, you cannot predict bugs. They will always delay your schedule. So there's definitely, you have a big handle on removing bugs at compile time so that you don't get them when you actually try to deploy the system. Then productivity is an issue. When software developers are writing a program, in the best case, you want them to focus on the application that they're implementing, the features, performance issues, and thinking about the software problem is complex enough. And programming, to some extent, to this date, is also distracting the programmer from the actual focus through various related problems, especially to concurrent programming, that sort of make it extremely difficult to stay focused for the actual things. And of course, these are not the only problems, so bugs and productivity are not the only issues that we are having. There are also management-related stuff for requirements, but we are really focusing on bugs and productivity here. So we've been looking at some of the business analyses from consulting companies, and they actually found out in a huge survey in 2008 that if you can optimize the development process and the maintenance of the software, you can actually reduce the costs of the entire project by more than 50%. Maintenance also includes debugging and all the sort of tasks that you have. And one really important insight from this study was that although we have developed a huge amount of programming languages in the recent decades, the productivity of the individual programmer is the same since '88. So we've seen many paradigms come. Obviously, it's really difficult to solve this productivity issue. With a lot of new languages, and we're still as productive as 30 years ago, essentially.
What was the measure of productivity that?
Oh, there's various different things. So we have the source here. So if you want to have a very detailed discussion on what the measurement is, you can look at this book. He describes it in a couple of pages how they measured it. But the general idea is that they take basically milestones. They set themselves milestones, and of course this is a very complex problem. It includes management stuff. So this is it's not an entirely precise measurement. Of course, it's an estimation. So don't take this as the most precise measurement ever. But it's definitely a good estimation of how at least large companies perceive the productivity of the developers. And definitely for the management layer, how they perceive their team is quite a big deal, actually. And of course, the argument that you can always test your software and have 100% code coverage is not in all cases helping you, because in surveys I found out that actually a lot of defects are not found by testing, even if your code coverage is high. So then we started to think, what is that we can do, or what is that we want to do to solve some of these problems? So we decided to implement an actor model object-oriented capability secure language. What that exactly is will be explained in more detail by Sylvan later on. And as we said previously, we really want to empower the programmer to get stuff done. So the compiler and the language should actively support the programmer in succeeding in this case. And our main focus is really correctness, because there's almost no point in continuing if you don't get it correct. And everything else is focused on performance and a couple of other points that we will talk about later. And the key is, it's about compile time guarantees. So the compiler needs to be able to fix all sorts of problems for you and to tell you about all sorts of problems. So the actor model, many people probably know it. It's kind of a very natural paradigm to express asynchronicity through sending messages. And asynchronicity is essentially used as a notion to express parallelism and concurrency. So we've implemented a language where actors are first-class citizens, so they're intrinsic to the language. It's not a library on top of a language that we built previously. Message passing is the only concurrency primitive, and we have another runtime guarantee on top that message delivery in the Pony programming language is always causal, which is quite an interesting and powerful thing because you can reason about the ordering of messages and how they are received by actors. If there is more interest on causality, we can talk about that in more detail later. The key thing is causality works without runtime costs. We will be here for the rest of the day, so if you want to pick our brain on this stuff, just approach us and we can talk about all sorts of details now in this case. We are fans of type systems, so we think types are awesome. Types are guarantees. And types allow us to prove properties about a program without having to run it. We can take a type system and we can look at the program and we can, for example, in the case of the Pony type system, prove that it has no data races at compile time. Otherwise we can throw an error. We cannot make that proof. The Pony type system has no null, so we sort of listen to Tony Orr in that case. And we have cheap runtime type information because we think it's quite important to inspect type information at runtime, and it's capability secure. Most of you maybe have heard about Mark Miller's work on capabilities, on E, etc. And those capabilities are really the party trick when it comes to data race freedom in our language, and we'll get to that later. So it's not like that we went down one single road and implemented a object-oriented language and then stopped. And we're also at the same time huge fans of various functional languages, and we thought it would be quite powerful to combine object orientation with some functional features like type expressions, polymorphism, pattern matching, the notion of mutability and immutability, the idea of having no globals, and all that, the very good ideas that come from the functional world. So when we started to draw out the implementation of the language and how we envision the language, we sort of wanted to have a completely from scratch design across the entire stack. So we have a low-level runtime, a high-performance runtime. We have high-level language features, like you know it from Python or all those classic fast prototyping languages. And the programmer experience in the end is really key. So how the programmer thinks about its application and how productivity is perceived and how the confidence looks in terms of is my application correct. Of course, implementation efficiency influences the language design. It's clear. Now, the cognitive load while programming tends to be, especially in the concurrent world, can be really high. And if you use a very, very sophisticated type system, that can be still the same. So now the question is whether you get a trade-off right between the cognitive load of the usual concurrent programming where you have to fix data races yourself, and the type system being usable enough so that you are actually more productive using a more complex type system. So the type system is one very important point here, and of course we have the syntax of the language, and we draw a bit on Python and Ruby. You will see it later in some screenshots and code samples that we give, and the ML family was quite an inspiration for us. we know capabilities, what we will talk in more detail. They are complicated, so it's not that you look at them and you understand them immediately. You have to get a little bit used to them. But the key difference is you can reason about capabilities locally. So you look at your piece of code, and all that you need to know can be seen and known from that piece of code. You don't have to know anything about the other parts of the application. And that is really a huge benefit, I think. So this is sort of a little bit the roadmap, and then I want to hand over to Sylvan to really maybe show what the internals are of the language, how it looks and how it feels.
Great. All right.
Maybe turn off the micro for me.
Let's get technical. So high-performance language runtime, we need that. Running on top of virtual machines is great for certain types of applications, but there are many types of applications for which it is simply not possible. There are performance guarantees that have to be made where you have to do a step better than that. Advanced type system features. Advanced type system features aren't just about being able to do fun, awesome things. They're also about performance. Being able to make those guarantees at compile time, that means there are no runtime checks required for very complex operations like message sending or changing capability types, freezing a mutable object as an immutable object as a no-op, for example. That's pretty cool. To do this all and make it useful to the industry programmer, it has to be C-ABI compatible. If we're not on a VM, then we're not taking advantage of the JVM's really impressive ecosystem, right? If we're going to go out there and do this, we need to take advantage of what we can, and that's existing C libraries. We're doing that bidirectionally. So we want to be able to call C, but we also really want to be able to have C programs or anything else with a C foreign function interface call into Pony as a library. Using LLVM as the compiler backend is just a huge win. I don't know if anybody's been able to use LLVM for a project, but it's a brilliant piece of software that basically handles your code generation, your optimization, and all of your backend architecture targeting on its own. It's great. It's a little bit painful to use sometimes, but it's brilliant. If you're interested, if you want to whip out the laptop and code while I talk, there's a sandbox online, sandbox.ponylang.org, where you can compile and run arbitrary code. And I'll talk a little bit later about why that's OK for us to let you run arbitrary code on our server. So, language runtime, message queues, message passing. In an actor model language, this is what it's all about, right? If your message queues are fast, if message passing is fast, if those are cheap abstractions, then using that as your sole concurrency primitive is a huge win. You're not dealing with mutexes, you're not dealing with semaphores, you're not dealing with all of these things that are runtime complications. Instead, if your message queues are fast and you can prove all these things work at compile time, you pay almost zero cost. We're going to talk about the actual underlying costs. One thing we've definitely learned from functional languages, obviously, is that memory allocation is a core bottleneck. Not just garbage collection, but the allocator itself. Haskell has a particularly impressive memory allocator in terms of how fast they can churn objects, because they need to in a functional language. So I'll talk a little bit about how our memory allocator works under the hood. But garbage collection in the actor world is hard. Really, really hard. Because you can't have a stop the world step. The whole point is to have concurrency across all of your cores all the time. All of your cores have to be churning real work. If you have to have a stop the world step and coordinate among those cores in order to collect garbage, now you get the famous JVM pauses. And we don't want to do this the way Azul has done it, although Azul's pauseless garbage collector is really impressive. They've done it using write barriers. Well, that's hard. They've also added read barriers, which even the standard JVM doesn't have. This means that the normal process of running code is constantly taking an overhead in order to deal with garbage collection that will happen in the future. So we want to do it without read or write barriers. And we still want to be able to collect across actors as well as individual actors, and we want to be able to garbage collect the actors themselves. And I'll go into how we do that. Obviously, work stealing scheduler. There's a great paper about 3 or 4 years ago called Work Stealing Proven Optimal. What a great title for a paper. I don't know, maybe it isn't, but it's a great title. And certainly Intel's had huge success with their work stealing scheduler in Silk Plus. I know that hasn't achieved the penetration that Intel has hoped for, but it's really impressive work. We have a little bit of a different take on the work stealing scheduler because of the way the actor model system works, and I'll get into that as well. So let's talk about message queues. Multi-producer single consumer queues, most of the time, are implemented with a gigantic lock And then in languages like Erlang, you get to pattern match over your message queue, which means you're going to do very complicated operations with your message queue while it's locked, and no one can put a message on your queue. So that has very serious performance implications. So we've done something a little bit different. Ours is a single atomic operation on push, no loops. 0 atomic operations on pop, no loops. It's an unbounded queue. If there's one thing TCP has taught us, it's that delivery is not an acceptable substitute for back pressure. Just because you've handed it over doesn't tell you anything. So back pressure has to come at a higher level in the system. You need to be able to talk about further down the line, I've done enough processing that I really am able to accept further input. So that's not at the queue level. The queues are unbounded. Previously empty detection on push is pretty nice. It's part of the single atomic operation and helps with the scheduling. If you know who Dmitry Vyukov is, he used to run a site called 1024cores.net, really interesting guy. He now works on the runtime for Go at Google. So, scheduler threads. Scheduler threads are another form of queuing because you're trying to have all these cores have a load all of the time. That's how you're taking advantage of the multi-core system. So in this case, they're not queuing messages, they're queuing actors with pending work. And here we have a single producer, but multi-consumer queue. It's the exact opposite. It's only ever going to push onto itself when it schedules an actor that was previously unscheduled. But because of work stealing, any thread, any core, might pop off that scheduler queue. So here we get 0 atomic operations on push with no loops. That's really good. But we take 128-bit compare and swap loop on pop. That's bad. Okay, admittedly, it's as far as we can tell in the research community the best case for a single producer multi-consumer queue. And that's nice, but it means that being careful about contention in the work stealing case is important. The scheduler has to make sure that if we're going to do work stealing, we don't have everybody trying to steal from the same scheduler thread simultaneously. If you limit that contention to one thread, one core stealing from one other scheduling thread on another core, then you limit the contention to 2 possible pops, which means you're limiting your possible compare and swap iterations to 1, which is great. Again, unbounded, also based on Dmitry Vyukov's pretty fun work. So, message passing. In Erlang, which is great language, don't get me wrong, brilliant language, in order to achieve the safety they need, messages are copied when they're passed. This can be expensive. You're talking about possibly very deep copies on very large data structures. In akka, or Scala actors, you can pass by reference. That's awesome. It's hugely faster. On the other hand, it's not very safe. You can very easily have many actors with access to the same mutable state, and you're right back with the data race problems that you had before you started using actors in the first place. And now you've got something that's functioning like a thread, and you've got a lock, and you're back to the same concurrency primitives that you needed back when you were using p-threads, or whatever your mechanism is. So here we're using the type system. And the type system allows us to guarantee that there are no data races, pass by reference, and combine the advantage of these two systems into something that's fast and safe. So, memory allocation. Actors have separate heaps. This is really important. You don't want to be allocating off the same heap, purely for speed reasons. On the other hand, we need to be able to share pointers across heaps, right? We're passing things by reference in messages. That's going to complicate garbage collection, as we can see. But what this does, having these separate heaps, is our amortized alloc cost is a single count trailing zeros. That's pretty nice. We actually have a cheaper amortized cost than the Haskell memory allocator. Pretty fun. Don't get me wrong, amortized cost. Every now and then, we're going to map from the operating system. We're going to take a hit from that. On the other hand, these days, operating systems, particularly Linux and FreeBSD, are doing a brilliant job on mmap, and that's pretty cheap these days, impressively cheap. We use an underlying pool allocator underneath the heaps for the runtime, so that we're using a combination of small and large slab allocators, similar to how JEmalloc, GCmalloc, some other systems work, kernel memory allocators. And it means we have no per-alloc headers, no coalescing problems, and I'll talk a little bit how that interacts with GC in a minute here. So, fragmentation. If we're not doing coalescing, are we just fragmenting all over the place? Well, we don't think so. I don't have a really great answer for this. As far as our benchmarks go, we seem to be doing a really good job because we've got these per size pools that are meaning that you tend to allocate off a small slab, and when there are free spaces, that's pushed to the head of a queue, and you reallocate off the same small slab. And as far as we can tell, we're controlling fragmentation pretty well. But this is an open topic. We're going to have to spend some time on this. We're cache line aware. This is critical. You don't want to have false sharing built into your memory allocator. That kills you. So we pay very careful attention to, is it possible for an object to be shared? If so, it needs to occupy a cache line of its own. NUMA. We're taking advantage of NUMA. Got to take advantage of NUMA. We're benchmarking on big NUMA systems right now. So underlying pools are allocated on local nodes. That's really good. Actors can migrate, though. Right? You've got an actor on a core, another core is idle. You're pulling that actor over there. All of a sudden, all this lovely local NUMA memory that you've allocated is running on another node. So we tried migrating the memory. That was a mistake. It turns out the operating system does a much better job of migrating that memory for you than you're going to do in the runtime, or at least than we've been able to do in the runtime. This is still an open question. To be honest, I hope it stays in exactly the state it is. I hope that the operating system remains the expert on this. I'm not sure that it will. We'll see. So, garbage collection, per actor garbage collection. Actors are GC'd separately. The actor that allocated a piece of memory is always the actor that's going to collect that piece of memory. Now, since we can pass by reference, this is going to get complicated, and we'll talk about that. But this means that it drastically simplifies the kind of garbage collection algorithm that we can use. And we take that a little bit of a step further. You might be familiar with safe points. When you're writing Java code, a lot of times you've got to pay careful attention to what the compiler is going to consider a safe point in your code. Because that safe point is also a coordination point amongst threads. And when all of your threads have hit a safe point, a big garbage collection cycle can happen, which means that at any safe point, your code may be halted for an indeterminate amount of time. That's a problem. So in Pony, garbage collection only happens between messages. It only happens when your actor is not executing a behavior. This means that you're never interrupted, and GC never happens when there's a stack. So we don't have to put roots on the stack. If you're familiar with GC implementations, keeping track of roots using shadow root systems or anything that you want, any other approaches you want to do, is the most expensive part of garbage collection. It's more expensive than tracing, which sounds crazy until you realize that heap mutation and execution and stack execution is having to mutate this stuff whether GC is happening or not. That's expensive, and we want to stay away from those things where we're paying a price when we're not actually getting anything done. So, we get to GC without ever looking at the state of another actor. It's fully concurrent GC. So if an actor decides, I want a GC, there's no, at that point, no coordination with any other actor, no coordination with any other scheduler thread. It goes through, it GCs, no stop the world step, nothing. We use a mark and don't sweep algorithm. That's nice. It means we never ever touch memory that's not in our working set. And I mean never touch. We don't look at the pointers. We certainly don't read the contents of them, which means we don't thrash the cache or even worse, swap on something that's pointless. We're getting rid of the memory. We don't want to read it. We do it with no read and write barriers, as I mentioned previously. Basically, at this point, nearly all GC algorithms use read barriers. Use write barriers, and some of them use read barriers. We're using a non-compacting collector, so there's no pointer fix-ups. We're never having to go back through the working set and fix up after copying. Of course, that's a problem as well. Copying collectors introduce really great memory locality, right? That's a huge advantage. So we try to control for this with that underlying allocator. Remember I was talking about per size pools and reducing fragmentation. So what we do is that memory that you drop, the memory that you're likely to allocate next is contiguous with the memory that you've kept. So instead of saying we're going to take the memory you've kept and put it all together, we say we're going to take the memory you've kept and future allocations will be contiguous with that memory. So far this looks like a win. I hope it stays a win. So cross-actor garbage collection. You pass a reference. Now how are you going to GC it? Only the one that allocated can GC it. What are you going to do now? And the answer is deferred distributed reference counting, which is a lot of buzzwords and means that basically when we send a message, we trace the contents of that message and we increment a local reference count for each of the things that we're sending. We don't care who we're sending it to. And we don't care about heap mutation. if some other actor has a reference to an object where we've allocated, we don't care how many times it appears in their heap, the classic reference counting problem. We only care that it's possible that one or more other actors has a reference to it, because if that's true, we can't collect it. So it turns out that doing that tracing and keeping track of those reference counts can be amortized really, really aggressively. And the fun part is what happens when we send out a message in the future. So I send a message to some other actor containing some pointer I've allocated. It turns around and wants to send it somewhere else. It looks at its own reference count, and it sees that it's been sent one reference to this thing. And it can't guarantee that it isn't keeping a reference itself. So before it can send this thing, it's got to invent a new reference count. So it's got to tell the owner that there's some more references. That's been a huge problem for distributed garbage collection for a long time. But because we have causal messaging, and message passing is our only concurrency primitive, we can invent new references and inform the owner that we've invented new references, send out our message to that other actor with no acknowledgement cycle from the original owner. None. We just deliver it, we go, that's it. We've invented new references, and we're guaranteed that the owner will receive the fact that we've invented new references before they receive a message from some future actor saying that they've deallocated some references, and so you can just go clean that thing up. So that's pretty fun. Another problem in distributed garbage collection is cycle detection, because it's been based on the number of references in a heap traditionally. But you'll notice when I've been talking about this, I keep talking about the number of references that an actor has to an object, but not objects to other objects. Objects don't have references to other objects as far as the garbage collector is concerned. It doesn't care. It doesn't care about the shape of your heap. As a result, there's no cycle detection. That's a big win. Distributed cycle detection is expensive. So we want to collect actors themselves as well as objects. If you've used actor model systems, Erlang, you've got to send poison pills in order to kill off actors. Same thing in akka. It can get problematic. It's basically manual memory management. And we all know how well that tends to work for us in C++. So we did it. We invented a system for garbage collecting actors themselves. It turns out it's the same system we use for Object-GC, except it's a little more complicated because actors can have references to each other. So we need a cycle detector. So how do we solve that? Do we introduce some locks and all that stuff in the underlying runtime? No, we don't want to do that. We want to stick with message passing and concurrency. So we have a system actor, an underlying actor that you don't have access to as a programmer, that is a cycle detector. And when actors block and change their state, every now and then they'll send a deferred message to the cycle detector saying, hey, I'm not doing anything right now, I'm stopped, and here's vaguely what the shape of my references to other actors might look like right now. No guarantees, I might have changed it by the time you get this message. And then that thing's got to detect cycles, and it's got to somehow consolidate in an eventually consistent way its view of the topology of the system with the real view of the topology of the system. And it turns out there's a really fast way to do that that takes advantage of causal message passing. I'll mention causal message passing quite a bit. What you do is you just send a confirmation message to all the actors in the cycle, and they all send an acknowledgement message back. It has no state inside of it. Well, it has an ID number, but they just echo that ID number back. They don't have to know anything about you as the cycle detector. They don't have to, there's nothing to keep track of. But that process determines whether or not the queue was empty when the original block message was sent to the cycle detector, and it means that you can say that this actor can never receive work in the future. You can prove that. We've got a mathematical proof. We published a research paper on this like you do. And that's quite fun, because it means we're able to clean up with a cycle detector in a way that's very efficient and very fast. Now we can GC actors themselves. Now we can spawn off millions of actors in a program, short-lived, long-lived, we don't care, without thinking about it, without managing it. And turns out that's a huge advantage. A lot of actor systems encourage you to for example, akka used to, don't anymore, tell you, try not to use more than one actor per core on your system. Sounds like a thread to me. So we say the opposite. Go nuts. Millions of actors is no problem. We've deployed some real-world system that use quite a bit more than millions of actors for a long-running system. So, work stealing. We can use any number of scheduler threads. We default to the physical core count, like you do. Turns out, actually, we can take more advantage of hyperthreading than we thought we could, so we might want to change that default. We're going to have a real look at that. We use those queues to manage it. Actors with pending work tend to stay on the same scheduler thread. That's important. It's important for cache locality. You don't want to move that thing unless you really want to take advantage of an idle CPU. On the other hand, if you have no pending work and you get a new message, we schedule you on the core that sent the message to take advantage of the cache locality of the contents of the message, since the actor's working set is likely not to be in cache at that point, since it had no pending work. So that's runtime. Well, not all the runtime, but some of the big features of the runtime. So now let's talk about the type system, because some of the features that I talked about in there are clearly useless without the type system, particularly without a data race-free type system. If we can't prove that you don't have data races, then all of that stuff goes to hell, and all of the garbage collection work just doesn't work at all. But we also want to make sure that the programmer has the tools they need to get their job done, not just to make the guarantees that they need for fast concurrent performance, but also to give them the features they want for implementing the algorithms themselves. And that means we need generics, we need type expressions, interesting typing, both structural and nominal, to solve all kinds of interesting typing problems. We want functional features, pattern matching, lambdas, partial application. This is important stuff. Languages that aren't offering that kind of stuff are frankly old-fashioned at this point. Capability security. This is a big one. It ties into the data race-free type system, but it is also about a long-running trend in security, starting in the 60s with operating systems like Kikos and Eros and Kyotos, which were capability-secure operating systems. And then going into languages like E or Caja, or frankly, ECMAScript 6. Sounds a little weird. That's a really common thing, right? We're talking about JavaScript here. But actually, ECMAScript 6 has a capability security extension, Mark Miller's work at Google. This is critical stuff. Security has become an overwhelming facet of our industry at this point. So, capabilities. Capabilities for data race freedom, as opposed to capabilities for security. So we do it with type qualifiers. So we want to express a few different things. Turns out there's 6 things. I haven't mentioned them all here. Clearly, we want to know if an object is immutable, right? We want to know if it's mutable, locally mutable. Because if it's locally mutable, then no one else can be mutating it. That's important. But then if we want someone else to be able to mutate it, we need to express something different, isolation. We need to be able to say, we can mutate it, but we know by reasoning locally that there are no other mutable references to this thing or to anything that it reaches that is mutable. So there's a boundary there. There's also opaque references, which turn out to be powerful. We'll talk about those in a minute. But capabilities ensure these basic principles. We're all familiar with it. If I can write to it, nobody else can read from it because I might be modifying it. And if I can read from it, nobody else better be writing to it because otherwise modifications might happen while I'm reading from it. These are the same thing. Yeah?
This sounds like locking.
It sounds like locking. Exactly. It sounds exactly like locking. Yeah, so we do this without locking. And what we do is we say, look, these are the same thing. We state it from each perspective because you can reason locally. And it's in the type system. If I have something that has a reference capability of val, which means immutable in Pony, the compiler has already guaranteed that nothing else can be writing from it. So I can read from it indiscriminately, and I can share it across any number of actors that can all read from it indiscriminately because we know it's globally immutable. Because that's an excellent point. Otherwise, you're going to do this at runtime. So we want to do it in compile time. We want to prove these things at compile time. Similarly, I want to be able to know that whether or not I can send something in a message. If I want to send something mutable, I need to be able to prove to the compiler that I haven't kept a reference to it. Because if I have, even if it's just a reading reference, I can't send it out because it's mutable and I've violated all my guarantees. All of these need to compile down to a no-op, and they do. Yeah?
You just said when I send a message to another actor, I'm not allowed to have a mutable reference after sending this object.
That's right.
But I'm allowed to have an immutable reference.
Yes.
But I think 2 slides before you, there, yeah, one more.
Here? This one?
Yes,
all right.
No other actor can read it, and an immutable object is readable.
If I write to it. If an actor can read from an object, no other can write from it. If I can write to an object, no other actor can read from it.
Yeah, but
I can read from it while you read from it. That's all right.
Yeah, but when I am sending an object to another actor, you probably can have the mutable one.
Only if you're sending them something that's isolated in order to prove that you haven't kept either a read or a write reference.
So I can only send a mutable object when I want to have the readable one.
Correct.
Still, or I have to hand it over completely.
Exactly.
Okay.
Exactly. So let's look at some code. Here's a TCP listener. It's sort of a common thing you need in some code. We're going to show a lot of different aspects about this. You can see from looking at it that the syntax is basically ripped off from a lot of other languages. It's a bit Pythonish, it's a bit OCaml-ish. Hopefully, it's a bit familiar. We don't want to frighten people off with syntax, right? That's not helping. So actor constructors are asynchronous. That's the first thing to take a look at. This is an actor. It's not a class. An actor is just a class that can have asynchronous behavior. It's not that different. But when you create an actor, you get a pointer to that actor immediately, but the constructor doesn't run. The constructor runs eventually, at some point. But because of causal message passing, again, causal message passing, we know that constructor will run before any future messages are received by that actor. So it's totally cool to delay the constructor. That's pretty fun. So actor behaviors are asynchronous too, behavior. That's just an asynchronous function. That's good. They can have synchronous functions as well because an actor is an object, but asynchronous functions are the fun part of the actor. So all the parameters to a behavior or an actor constructor have to be isolated or globally immutable, val, or opaque, tag. A tag reference is something where you have the identity, but you can't read from it or write to it. Turns out identity is actually a powerful concept, and in an object-oriented language, you can do all sorts of interesting things with that. Like, for example, what about using the identity of an object as the key in a hash table? That's pretty good. But you can do even more than that. Actors get typed as tag when you send a reference to an actor to another actor, because sending an asynchronous message is neither writing nor reading. That's cool. Means actors are integrated into the capability type system for objects, and they have the same data race freedom guarantees that objects do. So here you see string and U64 default to val. Lots of defaults. You don't want to be typing capabilities all over the place. Types can have default capabilities. You want to limit that cognitive load, as we say. But in some languages, string is a mutable type or is a immutable type, an immutable type. In Pony, types aren't mutable or immutable. Instances are, and in fact, references are. That's pretty powerful. It means that you don't have a situation where you're writing an immutable version of something and a mutable version of something. You write it once, and you can use whichever version you need in your program at that time. So notice here, we want to assign this notify that we received to a field and keep hold of it. But we've got to be sure that no other reference to that isolated object survives. So that's what consume does. It just says, this thing, we're going to kill it out of the lexical scope. This can't be used again, and we're going to consume it. So now we have a ref, a straightforward, sort of old-fashioned mutable object type that we've consumed from an isolated. So now we've passed mutable state to a new actor with no locks or runtime checks. That's pretty fun. So constructors are guaranteed to initialize all fields. We have no null pointers. It's a completely null-free type system. So we've got to be sure, before we call any more functions on this object, that we've initialized the whole thing. That's why notify listening has to be at the end here. We can't put it up earlier because we won't have initialized all the fields. It doesn't mean you can't call some functions on an object. It just means that the compiler understands that it's not a fully initialized object, so you can neither read from it nor write to it yet because it can't make any guarantees about what might be null or not. Well, that's cool. We've got a capability for that. So until it's fully initialized, it's a tag. Once it's fully initialized, it's a ref. Nice and simple. Again, it's about the instance, about the reference that has the capability and not the actual underlying object. We don't want a situation where by taking something isolated and making it globally immutable, by consuming it and saying, hey, this was the only reference that could write to it, it's gone, so now we can treat it as globally immutable because we know nobody can ever write to it again. Ooh, that's pretty good. But we don't want to have to go through all those objects and fix them up with some runtime check. Forget that. That's got to be a no-op at compile time, and it is. That literally compiles out to nothing. So capabilities are tricky. I don't want to lie to you. It takes some getting used to. Not as much as you might think. A couple of weeks, and usually people are pretty much good to go. But what Sebastian was saying about reasoning locally is the real key. It actually reduces the cognitive load on the programmer. These things are composable. Unlike in a threaded system where adding behavior somewhere can drastically change the whole nature of your system out from under you, here you know exactly what you're dealing with. You can reason entirely locally, which is nice. They're flexible, they're polymorphic. There's a bunch of stuff on capabilities we're not going to cover. Generic capabilities, viewpoint adaptation. What happens when I read a mutable field out of an immutable object? Well, it turns out you get something immutable back because immutability is deep. It's the only way it's useful. All those things are built into the language. They're pretty easy to get used to, but we're going to skip over them here. So Pony is generics, type expressions. If you're familiar with functional languages like OCaml is very big on type expressions, so is Haskell. Polymorphic functions. I mention OCaml a lot. I'm a huge OCaml fan. We are definitely influenced by the ML family. We want to make sure that we're as flexible as that. That's a very powerful and flexible type system. So here's a union type, string or none. Might be string, might be nothing. That's good. Like an option type. Here's a tuple. See the comma? So we've got two things. We've got a string is the first element, and something that might be a string or might be nothing is the second element. This isn't sugar. Scala, for example, has tuples as sugar for an object type, which is very useful because you need tuples, but can be problematic in other ways. Here, it's just built into the language. It's actually quite different from an object. It's more like an embedded C struct, sort of. And here's a generic, funnily enough, same line. It's an array of stuff. There's no special notation for arrays. They work just like all other generics. In fact, arrays are written in Pony rather than being a language primitive. All right, traits. This isn't type expressions, but it's up there at the top there. So stringable. Stringable, in this case, I'm not showing the code for stringable, but it's something that you can call string on. Get a string out of it. Could be anything. Here we're saying this option is stringable. So that's nominal typing, right? We're saying we're definitely of this type. It's like Java interfaces. But we also do structural typing, like Go. So we have both traits and interfaces, where an interface, as long as you provide those methods, you are that type. That's pretty powerful. Go uses that extensively. If this reminds anybody of type classes, that's great. I hope it does. These are effectively object-oriented type classes. So type parameters have constraints, right? Here we have some hash function that has to be a globally immutable hash function on an alias of A. Okay, that's some weird syntax. I'm not going to dive into that too much, but it turns out aliasing is really interesting with capabilities, because if I have something isolated and I take an alias of it, I can't get something isolated. And I'm going to have to speed up as well. So I get something tagged back. So that's interesting. Aliasing is powerful. So here's some more generic stuff where we're specifying type aliases, where we filled in some of the type parameters. And here we filled in a type parameter of a different type, where we have to make sure that we can compare on structural equality for this type of set. And to do that, we need to make sure that the thing in the set is hashable and comparable. Hey, and intersection type. Intersection types are extremely powerful, useful. Being able to know that something is two different things. Really good stuff. So intersection type. So I talked about this a little bit earlier, both straight traits and structural types. Implementation-wise, structural types are quite different from how they are if you're used to them from Go or Scala. Go, for example, sometimes needs to create a vtable on the fly. That is problematic. Scala's structural types are quite slow because they have to do some complicated dynamic dispatch on every dispatch call. We just have a single vtable for everything. Virtual dispatch is always a single array offset. It's always as fast as a non-thunked C++ object for virtual dispatch. It means that the indirect branch predictor on x86 hardware is basically eliding the cost of a virtual dispatch call. This is a huge win. It means that absent inlining, this is fast as non-virtual dispatch. Runtime type information is cheap too, for some of the same reasons. So if you're familiar with Cohen contravariance on type parameters in Scala, sometimes people get really upset about how that works because it's complicated and it's hard. We use structural types. I'm going to not go into this too deeply, but basically we have invariant types, type parameters, and structural types allow us to provide the interfaces that we need without that extra cost and that extra cognitive load. So an array U8 is not a subtype of array stringable, but it is a subtype of read-seek stringable. So if you only need to read from it, you're good. And that avoids the type system hole that you might be familiar with from Java or Eiffel. So pattern matching. We need pattern matching. Got to go fast. Here's some pattern matching. Looks like OCaml. Yep, here we go, matching two things. It's tuple. That's good. Pattern match on type. Pattern match on structural equality. Uses the EQ method of the underlying type because we're respecting the object-oriented encapsulation boundary. We're not doing automatic decomposition of patterns. It's not like case classes. You can do pattern matching with any type in Pony. And obviously, don't care. Hooray. You'll notice it has an else branch. All control structures in Pony have an else branch because everything in Pony is an expression. Everything can return something. A while loop that never executes its body needs to be able to return a value, so it has an else branch. So lambdas, partial application, anonymous types. We generate anonymous types for object literals, capture scope, everything that you'd expect to do. Because we're doing all this ahead of time, compile time, we can also detect when you're not capturing anything out of the environment and then your lambda has no memory allocation. It's equivalent to passing a function pointer in C. Really good speed there. There's some partial application where we're actually creating an isolated closure on this that we can then pass that closure to another actor to be invoked asynchronously elsewhere. That's pretty fun. That's what recover does. That's something I'll glide over too. Recover lets you do powerful stuff where you have a complex mutable object graph and you need to get something isolated out the other end, or even something globally immutable so that you can have cyclic immutable data structures. Pretty cool. Here's some lambdas we use in our test suite. There they are. So capability security. I'm going to go over this pretty quick because it's a tough one. But the combination of the address, an unforgeable address, and a set of permissions on that address are capability security. This is pretty good stuff. The amount of security that this can provide in an application is impressive. Please look at the work on Caja and ECMAScript 6 and other languages. If you're interested in this kind of stuff, E is probably my favorite, although it hasn't been around for about 10 years, 15. So the CFFI can break the capability model. Remember when I was talking about executing arbitrary code on our web server? We can let you do that. But the CFFI is the only thing that can possibly break the capability security model because the compiler can check everything else. No one's here in C, it can't check anything, right? You made a call to C, hey, congratulations, I'm going to stomp on some random memory address and kick your dog. There's nothing we can do about that. But what we can do is establish a trust boundary by telling the compiler what packages are allowed to use the foreign function interface and everyone else isn't. So on the web server, we don't want you to access the file system, so we don't let the file system do FFI. We don't want you to access the network, so we don't let the network package do FFI. Turns out we also don't want you to write random FFI code, so we don't let your package do FFI either. And other than that, go nuts. You can use timers, you can use all kinds of FFI on the system safely because we've established a trust boundary, because it turns out FFI is also the boundary between the program and the operating system. And that's the thing you need to protect. So the trust boundary is actually clear, which is interesting. CABI compatibility, right? We got to be able to call it. We don't want to be able to we don't have to parse headers or have bindings or have all kinds of FFI overhead. It is ABI compatible. We literally link to C libraries and just call out in the same way that C does. We can also generate a library from Pony code, including writing a C header file for you, so that you can call into Pony from C or C++ or Python. Python can call C, so that's fun. And we handle, we can link libraries directly from Pony source. So here's an example, little @ sign. That's FFI. There we're returning an event ID. There we're linking a bunch of libraries to use SSL. And even on OS X, we're saying, hey, prefer LibreSSL if you can find it. And that's all done in the source code. We can even initialize, shut down C libraries at program startup and shutdown. Sometimes you have to, unfortunately. Yeah, generating a C header. LLVM. It's brilliant. Come on, it's insane. It also means that right now we only target x64. That's not that great, right? Well, it turns out already there's someone in the community porting to 32-bit x86. Sebastian started an ARM port. once we've have a 64-bit ARM port and a 32-bit x86 port, we should be able to do a 32-bit ARM port. That's pretty good. But more interestingly, there are all kinds of new architectures, particularly heterogeneous computing architectures. The LLVM is going to allow us to target, because all that hard work goes into LLVM. And our retargeting is a question of minor modifications to the runtime. And it might sound like, it can't possibly be that good. It is that good. That's LLVM. It's awesome. The future, capability secure mirror-based reflection. You'll notice I didn't talk about reflection. Yeah, we're going to have it, but we don't have it yet. Reflection in the context of capabilities is complicated. Gail Bracke's paper on mirror-based reflection is really critical on this. Mark Miller's work on capability security is really critical on this. Types parameterized on values. You might be familiar with this from being able to do that in C++, for example. It's a bit like dependent types in Agda, but not going down the dependently typed system hole. Package manager. Dear God, I wish we could just use someone else's package manager, but if anyone has any suggestions, that's great, but we don't seem to be in a position to be able to do that. Profile guided optimization, that's going to be fun. Distributed runtime. Sebastian did his master's thesis on taking Pony and extending the runtime so that it doesn't just schedule across multiple cores on the same machine, it schedules across the cores, across your cluster. You don't change your program, but it spreads out across your entire cluster and runs. That's vaporware.
With the same guarantees?
With the same guarantees.
Really?
Yeah. Warning, vaporware. We have a prototype. That's cool. But this isn't something we're shipping right now. We're hoping to have this available later this year. Don't hold me to that. But there's all kinds of interesting stuff you can do with that. The heuristics for scheduling are complicated and interesting. But it looks like we have a model that is pretty good for this. We also maintain our causal messaging guarantee in a cluster. That's exciting. So how to get involved. It's all open source, BSD, 2-clause. Website, IRC channel, come bother the hell out of us. We have a mailing list. Sometimes we even answer mail on the mailing list. That's occasional. But we are always answering stuff on GitHub issues and IRC, of course, right? Like, that's where you really want to go, to be honest. Please, we're looking for people to write programs in Pony. We're looking for people to work on the standard library in Pony. Standard library covers a lot of cases right now. Not enough cases. Standard libraries always need to be bigger. You want to work on the compiler? Come work on the compiler. It's open source. Want to work on the distributed runtime? And so contact us. Get in touch. Thank you very much.
So we have time for 2 short questions. I think that we are running out of time. Maybe someone?
Someone mentioned it already in the talk, but you really think that an ordinary programmer is able to deal with all these capabilities, stuff, and so on?
So that's something we've definitely worried about. But so far, our user community is growing pretty fast, and we actually ran this by students at Imperial College in London. And the results were much better than we expected. And that's why we kept talking about reasoning locally. People, often, it seems the pattern is to dive in, think you've got it sorted, code for a while, and then come back and say, I don't understand these compiler error messages. Why can't I do this? And that tends to go away after about a week or two, where people get the hang of it. The compiler tries to hold your hand as much as it can. And then the real benefits come. That ability to reason locally and the composability comes to the forefront. And then, yeah, we've had remarkably few questions about capabilities after that initial getting used to it period. Don't get me wrong, it's something that we were quite concerned about, especially because there can be some complicated issues with things like reading a mutable type out of an immutable type and getting your head around that. But so far, yeah, seems to be the case.
Also, actually, default capabilities are playing an important role here.
Yeah.
So I think we have a standard library which is roughly 12,000 lines of Pony right now. And we have 85% of all annotations are default capability. So it's not like the programmer is overloaded with having to specify a type specifier on everything.
Yeah.
Another question. You've talked about all the benefits of the type system, and it's true for sure. But the type system also restricts you, because you have to convince the compiler and the type system that your program is really correct.
Yeah.
So
You have to convince it you know what you're doing.
Yeah, right. So
Yeah.
sometimes it restricts you too much. So that you have to write around somehow the type system to do what you want.
Okay.
So the question is, do you experience such problems that you come to points where you see, okay, now I have somehow an isolated object and I really want another object here, so what do I do about that?
No, is the short answer. It turns out flexibility in a type system is the real key to preventing exactly the situation you're talking about. And it turns out the thing that I personally use a lot in my Pony code is structural types. Being able to say, you know what, I'm just looking for something that kind of has a shape like this, and everything else I don't care about, stop bothering me, is really powerful. It's something I love about Go, for example. I think Go is a great language.
I'm a Go programmer.
Hey, all right. And when it comes to capabilities, though, and saying, oh, I have something isolated, oh, but I just really want to share it with two different actors. Turns out, no, you don't. You really don't want to share that with two different actors. And having that enforcement at the capability level is actually just a huge boon. Every time I think, oh, if I could just get around this, it turns out I'm just wrong. That really what I wanted to do was make something immutable and share it so that I could pass it around lots of objects and lots of actors and avoid all of the data race problems. So I would say for the first part of your question on generalized type systems, structural types and intersection types are your friend, because they express that kind of don't give a damn that we love about Python and Ruby, where we're saying, look, I just want to be able to call this foo method. I don't care about anything else. That's important. That's powerful. And then with capabilities, yeah, just don't ignore them. Turns out they're your friend.
And somewhat relates to my first question that when is the programmer at a point where he or she can really design such a Pony program that really uses the capabilities in a correct somehow way? So that really makes sense, because I think, okay, understanding this, okay, something may take 1 week, but really writing programs that really make use of this in a correct way, I would say take you some more time. Right?
I agree with that. Concurrent programming is not something that's trivial. I think it's a lot easier in this system than it is to have the same problems when people are trying to deal with semaphores, locks, condition variables, p-threads, that kind of stuff, or even Java synchronize, which is problematic in itself. I think this is actually a lot simpler than that for the programmer, but I'm not saying that it's instantly going to happen. On the other hand, the one piece of advice that I keep handing out and have for a couple of years now on people using earlier closed source versions of this is, instead of thinking of an actor as a unit of parallelization, think of it as a unit of serialization. What goes in this actor is only the things that absolutely have to be serialized, because it makes a serialization guarantee. And everything else, put in another actor and let it just go out there and go crazy. And as soon as people make that jump, then they start thinking really clearly about the things they're going to need to send and the things that they're not going to need to send. And more importantly, the things that they're going to pass along to another actor, i.e. isolated data that needs to be mutated, and the things that they're going to share, things that need to be immutable, shared amongst the whole system, even if you're going to update them later, because you're going to have some change in that thing and then need to inform everybody. But with zero-copy message passing, that's okay. You get to do that. It's not the problem that is in Erlang where you're copying it across a crap load of processes. Instead, boom, share the pointer with a bunch of actors. It's okay. You're good to go. I don't know if that quite answers your question, though. I hope it's a little bit.
Another simple question. How fast is the compiler?
So our goal is to compile code as fast as Go, because Go is the absolute champion at compilation speeds. We don't compile code as fast as Go. On the other hand,
Are you as slow as Scala right now? Or?
no. I was going to say, oh dear God, no. No, we're faster than C. So we're faster than C. We're way faster than C++, where obviously everything's faster than Scala. No offense, Scala programmers. This is a known problem, right? And the thing that's holding us back in terms of being able to compete with Go for compile time speed is optimizations. And it's because we do really extensive whole program optimization using LLVM. So on a large-scale project, 90% of the compile time for Pony is optimization. This is post-code generation optimization. It's the equivalent of an expensive link time optimization pass. The advantage that this gets us is we're doing really aggressive whole program optimization. It's pretty fun just how much extra speed that gets you. Now, I don't want to scare you off by saying, oh, 90% of the time. It means that a big project is compiling in, say, 10 seconds instead of, say, 1 second. So we're dealing with things that are all right. On the other hand, Go programmers go, ha, 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 I compile with optimizations in 2 seconds. So
Yeah, but it's only single pass, so.
exactly, exactly.
Yeah.
Okay, so thank you very much for the talk.
Thank you.
Also for the interesting Q&A session.